Welcome everyone in the problem solving session for week 9 for the course Traffic Engineering. My name is Tanu Singh. I am a PMRF scholar at Department of Civil Engineering, IIT Kanpur. So in today's session, first I will summarize all the lectures of week 9. Then we will discuss some of the practice questions and solve all your doubts. Okay, so now we are starting with summarizing the lectures.
So today we will be firstly discussing the car following theory, which is a fundamental concept in traffic flow analysis. So when a vehicle moves along a lane, each driver is constantly making decisions. So in particular, the driver of a following vehicle tries to balance two things. Firstly, maintain a safe distance from the vehicle ahead, and second, to try to travel at a desired speed. Now, this behavior or depends upon what the leading vehicle is doing. So, if the leading vehicle accelerate, the following vehicle may also accelerate, and if it slow down, the following vehicle must respond accordingly. So, this overall, car following model or car following theory is a continuous control process where driver adjusts speed and spacing for safety and efficiency. So here is basic two things are there. Firstly, maintain a safe distance, and second, to achieve a desired speed depending upon whatever the leading vehicle is doing. Okay. So next is space headway and its importance. So the space headway, also known as the distance headway. So this is simply the distance between two consecutive vehicles. That is the distance between the if the two vehicles are traveling. For example, these are the two vehicles. This is the first one, and this is the second vehicle. That is the two successive vehicles traveling, then the distance between both the vehicles, front to front distance, not the back of the leading vehicle and the front of the, but it is front to front distance is the space headway. So this includes vehicle length, this vehicle length, and plus the clear gap between the two vehicles. So why this is important? So, because it directly identifies three key aspects. Firstly is safety, second is traffic flow and capacity, and third is level of service. So, if spacing is large, driver may have more freedom and the traffic condition is comfortable. But as spacing between the two vehicle decreases, the driver needs to be more cautious, and the congestion may also occur. So spacing is closely related to also is related to the density, and together with speed it determines the traffic flow. So managing spacing properly is crucial for efficient and safe traffic movement. Now comes the pipes car following model. So this model is based upon simple idea that this, as the speed of vehicle increases, the safe following distance should also increase. From this concept, the model defines both a minimum distance headway and minimum time headway. So this is the distance between the two consecutive vehicle is, in terms of space, is space headway, whereas in terms of time, how we calculate in terms of a time headway, if we mark a point, for example in the road section here, when the first vehicle front crosses this point, and then we take a measure the time when the second vehicle crosses the same point, so that difference is time headway. So here this model defines both the minimum distance headway and minimum time headway. As important observation from this model is that while a distance between vehicle increases with speed, the time gap between vehicle tends to decrease. So when we compare this model with real world data, we find that it actually works quite well for moderate speed, but it is less accurate at low or very high speed. So still, due to its simplicity, provides a useful understanding of driver behavior, that if speed increases, then we have to increase the safe distance between the vehicles. But since this model has some limitation, that it works only well with moderate speed, not with low speed or high speed. Now coming to Forbes model. So uh, so this model is based on the concept of driver reaction time. It assumes that when the leading vehicle slow downs, the following driver needs some time to perceive the situation and then react. So the minimum headway depends upon both the thing, the driver reaction time and vehicle length and speed. So the results from the Forbes model are quite similar to the Pipes model. It also shows the distance headway increases with speed, and while time headway decreases. From all these models, we conclude that the traffic flow is most efficient at moderate speed. At very high speed, drivers do not strictly follow each other, which reduces the overall efficiency. And these car following models are essential because they form the basis for traffic simulation. Whenever we have to simulate the traffic or create a similar situation, we need to follow one of the car following model that describes the real world data. So these car following models are important for traffic simulation or whenever we are designing a new road or doing the traffic management analysis. And now coming to the General Motors model. This is the General Motor car following model, which has significant advancement over the earlier models. These models are particularly important because they are based upon the extensive field experiments, and so they reflect the real world driver behavior more accurately as compared to the previous models. And another key contribution is that it helped to bridge the gap between the microscopic behavior and the microscopic traffic behavior, where microscopic deals with the individual vehicles, whereas macroscopic deals with the traffic stream as a whole. So the basic idea here is very simple, that the driver response depends upon two things. First is stimulus, which is the relative speed between the leading and the following vehicle, and the second is sensitivity, which depends upon how far the vehicles are and how fast they are moving. And depending upon this stimulus and sensitivity, we get a response. So the response is in terms of whether the following vehicle should accelerate or de-accelerate its vehicle. So the the response is the function of both. So the response is function of both the stimulus and the sensitivity. Where stimulus is the relative speed between the two vehicles, whereas sensitivity is the external factors. Okay, so that are sensitive to the drivers, depending upon the speed, what is the particular speed of the following vehicle, what the spacing is between them, and the responses whether the following vehicle has to accelerate or de-accelerate. So the General Motors have generational models. So first we will discuss the first generational model. So firstly, in this model, the response of the following vehicle is directly proportional to the relative speed. So in the first generation model, we have the model has taken that the response is directly proportional to the speed and sensitivity is assumed to be constant. So if the leading so this is the formula where x double uh, d is the acceleration, whereas the alpha is sensitivity, and this is the relative speed. The n plus 1 is the following, whereas n is the leading vehicle. So the relative speed between the vehicles are directly proportional to uh, the response is directly proportional to the relative speed, and the sensitivity is assumed to be constant. So if the leading vehicle is moving faster, the following vehicle will accelerate. If the following vehicle uh, uh, is faster, it will deaccelerate to maintain its safety. So, and if both are moving at constant speed, the following vehicle will continue at the constant speed. So, this defines the acceleration. So, when both are moving at constant speed, the acceleration will be zero. So, the following vehicle will maintain its constant speed. Now, based upon the field observation, it was found that sensitivity is not really constant. It actually changes depending upon how close the vehicles are. So this led to the second generation model. So where two levels of sensitivity were introduced, that was alpha 1 and alpha 2. So when the vehicles are very close, drivers are more alert. So sensitivity is high. When vehicles are far apart, the sensitivity is low. So but still this model had a limitations, that was deciding exactly when to switch to the high sensitive, since we have assumed the sensitivity to be constant. So when to assume it to be high and when to switch it to the low sensitivity was difficult to define. So this model has this limitations. So and it also had a limitation in the terms, like for example, if we assume that the leading vehicle had the speed of 120 and the following had the speed of 100, and similarly but the space headway between them is 50. We are just taking two examples, and in the second case the speed is same. The leading vehicle has 120 whereas following vehicle has 120, but the space headway between them is 500. So in both the cases, when we put these values in terms here, so here the acceleration will get same value for both the condition. But as we can see, if the spacing between vehicle is less, it should be more sensitive, whereas if the spacing is more. So in this example, case 1 should be more sensitive, which is not captured by generational first this was captured first and second model, because here we have though we have two sensitivity when we are close or when we are far, but here the problem was that we don't define when we switch to two different sensitivity values. Now coming to the third generational model. So to solve this limitation, we have third generational model. So instead of fixing the sensitivity value that was to be kept constant, here we have assumed that sensitivity depends upon the distance headway. So this means that that as the gap between vehicle decreases, sensitivity increases, and as the gap between the two vehicle increases, the sensitivity decreases. So here the sensitivity for if we take it as alpha, so here the alpha was alpha naught divided by the space headway, but which is been as shown here. It is the function of space headway, that is inversely proportional. As we can say, smaller gap higher sensitivity, larger gap low sensitivity. So this provided more realistic and continuous representation of driver behavior. But still we have the issue of the we can explain through example. So if we have, so for example, in the case 1 we have the space headway as 100 meter, whereas the speed of the first vehicle was 30, whereas the speed of this the following vehicle was 10. And in other case again the space headway was same 100, but the leading vehicle had the speed of 130 and the following vehicle had the speed of 110. So if we assume, if we are taking the relative speed, we get it as 20. And uh, similarly, if we take the distance headway, we get 100. So in both the cases, we get 20 by 100. But here, as we can see, if the speed is more, so the deaccelerations should be more, or the sensitivity should be more. So this was the limitation that was present in the third generational model. So to accommodate this limitation, where the case 2 is more more sensitive, but it does not the model, the third generation model does not capture the sensitivity issue that still the model has, we have fourth generational model. So fourth generational model includes the speed of following vehicle. If we include the speed of following vehicle, that is either 10 or 110, so we will know the sensitivity, how more sensitive a response should be. So to accommodate that, the fourth generation has the speed of vehicle included in its the model, where you can see this term is the speed of the following vehicle. So here the sensitivity has both the distance headway and the speed. So if a vehicle is moving at higher speed, the driver will react more strongly to changes in the leading vehicle motion, even if gap remains the same. So now sensitivity depends upon both the spacing and the speed. This makes the model more realistic. So further coming to the fifth generational model. So this is the fifth generation model is the generalized model. Here we have the two new parameters, that is distance exponent and speed exponent, but that is the power of M and L. So this allowed the model to be more flexible, meaning we can adjust how strong spacing and speed influence the driver behavior. So an important point to notice that the all the earlier model from first to fourth are actual, they are special cases of this. If in the first generation model both the value of M and L are 0, whereas in the third we have the M as 0 but L as 1, and in the fourth generation we have both M and L values as 1. So by choosing a specific values of these exponent, we can produce the earlier models. So in summary, the general motor model show how the driver response depends on the three main characters. First is relative speed, then the distance between the two vehicles, and the speed of the following vehicle. So because of this flexible and realism framework that this model provides, this model is widely used in traffic simulation and traffic analysis. So this was about the how the improvement or advancement has been done in the general motor car following model. Now coming to linking microscopic and macroscopic models. So uh, here the key question is, can microscopic vehicle level models like General Motors car following models be linked to the macroscopic traffic models that describe speed, density and flow that we have already discussed in the previous lectures. So on the microscopic side, the General Motor or JM model tells us how a following vehicle react to the lead vehicle based upon the relative speed and the spacing. Where we have seen the general formula for the GM model was this. Here the Xn and Xn are the position of lead and following vehicle. The differentiation of these position are speed, and further differentiation is the acceleration. Alpha naught is the sensitivity, and the ln are sensitivity exponents. And on the macroscopic models, we have already seen the macroscopic models that were Greenberg models, green shield models that describes the speed density relationship. That was really both based upon the macroscopic factors, whereas microscopic models consider the microscopic parameters such as distance, headway, or relative speed. So the question is, can we see a connection between these two microscopic and macroscopic traffic patterns? So to make this connection, we consider a steady state transformation where traffic is following smoothly and all vehicles behave consistently. So we make two key substitutions. So where the speed is taken as mu, whereas the difference between the position is taken as 1 by k. So this means the following vehicle speed becomes the space means speed, and the spacing between the two vehicles is replaced by the density, inverse of density. So when we apply these substitutions to the third generational model, we obtain a Greenberg's model. So where the acceleration is mu is equals to mu naught, where that is ln kj by k. So when we put these values, that is differentiated, and then we get the model that is kj by k. So this is the whole description how we get the Greenberg's model has been discussed in the lectures. So this is fascinating because how we convert the microscopic sensitivity to macroscopic speed, and that is that they both correspond directly to each other. So this is essentially what each driver does individually shapes the overall traffic flow. This is a strong and concrete link between the microscopic and microscopic perspective, where the sensitivity is the microscopic speed. Microscopic speed was the overall speed that was present in the particular traffic model or traffic condition. Now coming to the generalized fifth generational model. So as we have seen, the generalized The fifth generation model allow us to adjust two exponent, that is L and M, to capture a wide range of behaviors. So as we have seen, this was the model where acceleration of the following vehicle depends upon the relative speed and space headway, and also the speed of the following vehicle. So by choosing different values of L and M, we get different macroscopic models. If we keep L is equals to 1, whereas M is equals to 0, we get Greenberg's model. Whereas if we keep L is equals to 2 and M is equals to 0, we get green shield model. Only we have to pay attention that the speed is become as the speed of the following is become as the macroscopic speed, and the difference is the 1 by k. So if we put those values and also the L and M values, we get the corresponding Greenberg and Green model. So this unified form demonstrate a powerful link. The same microscopic model with appropriate parameter choices can describe different macroscopic traffic behaviors. So, why this is important? Firstly, it allows us to predict traffic pattern based upon the driver level responses, and also analyze safety and minimum headway requirements. Also estimate traffic capacity and simulate flow under varying conditions. So, from an individual vehicle behavior to overall traffic flow, the GM model provides a bridge between the microscopic actions and macroscopic merits. So, now coming to the traffic stability in car following. So, as we have discussed, the car following model is all about the vehicle react to a vehicle in front of it. The behavior of the following vehicle is crucial for the overall traffic stability. We recognize, we categorize behaviors as either stable or unstable. In stable conditions, the driver reacts quickly with normal sensitivity, leading to smooth acceleration and deceleration, whereas in the unstable behavior, the driver mainly occurs when the reaction times are high, the driver overreacts, and there has to be strong acceleration or braking to be applied. So the two main factors that influences the stability of the traffic are, first, the product of the reaction time and sensitivity, which we call it as a C factor, and second is number of vehicle in the car following stream. So a single following vehicle behaves differently than a line of multiple vehicles, and the difference is critical to understand the traffic stability. So here, when the reaction time is low and the sensitivity is low, there is smooth acceleration, deceleration. That is the stable behavior. Whereas when the reaction time is high and the sensitivity is also high, then driver overreact and there is large acceleration or sudden brake is applied. So that is unstable traffic behavior. Now coming to the local versus asymptotic stability, asymptotic stability. So here firstly we go with local stability. So local stability considers just one lead vehicle and one following vehicle. Here we observe three possible oscillation pattern, where first is the non-oscillatory, where no oscillation is done, vehicle maintains smooth movement. The second is damped oscillator, where the it some oscillation occurs initially but diminishes over time, eventually it stabilizes. And third is increasing, where oscillation grows larger over time, which is a sign of instability. And the In the asymptotic stability, we consider a multiple vehicle in a line. So it is the non-oscillatory behavior is unlikely in this case because two outcomes are possible. Uh, First is damped oscillatory, where oscillation diminishes and the traffic stream stabilizes. Whereas in the increasing, the oscillations grow and may result in collision downstream. So this highlights how sudden changes by the lead vehicle can ripple through the traffic stream, especially in the congested condition. Now this was all about the General Motor car following model. Now coming to the Vendeman car following model. So here the model that is widely used in traffic simulation globally is the Windeman car following model. So this model is based upon psychophysical aspects of traffic behavior, capturing how driver perceive and react to surrounding vehicles. So there are two versions, Windeman 74 and 99. In Windeman 74, it is mainly developed for the urban arterials, whereas 99 one is developed for freeways and in general situation with more parameters to make it more realistic. So the model defines four driving states. First is driving, free driving. The driver is unaffected by other vehicles that are in the traffic stream and it travels at a desired speed. So it is free driving. Second is approaching, a condition that is when the driver slows down to match the lead vehicle, maintaining a safe distance between two. Third state is following, where the driver maintains this speed and spacing without deliberately applying acceleration or deacceleration. So this is the following state. The fourth state is braking, where medium or high deacceleration is applied when when the spacing falls below the desired safety distance. So these are the four driver behavior states that model has defined. First is free driving, that is unaffected, approaching where it matches to the leading vehicle. Then the third one is it unconsciously maintains speed and safe distance. And fourth is braking, where the medium or high deceleration is applied to maintain a desired safe distance when the spacing is below safe distance. So now coming to the more detailed of this model. So it has a one important feature, that is perpetual threshold. So, unlike traditional models that assume a driver react to even small changes, the Windeman model recognizes that driver responds only when stimuli exceeds a certain threshold. That like relative speed or distance have increased a particular threshold, then only a driver reacts or we can see a response. So the car following behavior is divided into zones. First is the no reaction, where no action has been taken. Second one is unconsciousness, where minor adjustment is done. Third one is the braking, where deceleration is done to maintain safety. And fourth is collision zone, where it is below the minimum safe distance. So these are the four zones of car following behavior. So the thresholds are like STV, CLDV, OPVD, and STX, which defines when these reactions occurs, like uh, whether there is no reaction or there is a minor adjustment. These are the threshold that are being defined. So and then the model parameters, the Windeman 74 uses three parameters, that is average Standstill distance, additive and multiplicative safe distance. Windeman 90 is more detailed one, and it uses 10 parameters including the headway, speed, oscillation, acceleration, behavior and more. The key takeaway is that the Windeman model is highly realistic but needs local calibration to replicate the actual traffic behavior in simulators. We need to get more parameters to get the actual traffic behavior in the simulated conditions. So this was all about the car following theory. Now moving ahead with the traffic simulation. So starting so this traffic simulation is a system that is collection of entities interactive interacting to achieve a particular goal. So in this context of traffic, these entities include vehicle, pedestrian, traffic signal, road, traffic police, and channelization devices like island. So these different entities interact with each other to get a particular goal. Here, the entities are vehicle, pedestrian, signal, road, traffic police, and islands. The purpose of traffic simulation is to analyze how the system performs in terms of safety, efficiency, delays in signals, the emissions without disrupting the real world. Simulation helps us to plan, design, and manage the traffic system efficiently, and it provides a safe, cost effective way to test changes before implementing them on the road. So, whenever we want to analyze any of the safety efficiency of a particular roadway conditions without disrupting the real world traffic, we try to simulate that same condition and check and analyze the parameters, or whether or if we need to plan design a traffic system that is to be constructed. On that case also we do the traffic simulation, and it this and doing simulation helps us to do these analyzing or planning or designing thing more cost effective way, and that is a risk free way, because if we are going to build a particular infrastructure or we are moving particular thing, we can't do directly on the real world because that is a risk to be taken. Therefore, before implementing on the real condition, we try to simulate similar traffic condition and check on that, do the test on that, and then apply on the, if it works, we apply on the real world on the road systems. So the approaches to study a system. So we have two main approaches. Okay, the first is experimenting with the actual system. For example, installing signal at a junction and observing its impact. However, this can be costly, disruptive, and sometimes unsafe and infeasible. Second approach is using a model of the system. So instead of the real system, we create a physical or mathematical model. Physical model can be replica of for visualization or training, while mathematical model uses logical or quantitative relationship. So this allows us to test multiple alternative safely and efficiently. So these are the two way these we can study a system. So if we do in the actual system, then we that could be sometimes costly and disruptive, whereas if we want to do using a model of the system, that or the replica of the system, there is two types. First is physically, where we do it for visualization or training. If we want to build and we have to just visualize it before constructing or plan or designing on the real road, we do the physical model. And when we have to do the analysis Then we do a mathematically modeling. Now coming to the classification of simulation models. So simulation models can be classified into three ways. First is time based. So here static models capture the system at a particular moment, ignoring time like peak or traffic flows, and in the dynamic represents a system as it evolves over time, showing how traffic changes hour by hour. So these are the time based. Second is the randomness based, where it is deterministic models that use here we use the exact relationship with no random variables, whereas in stochastic it includes the randomness with variables following the probability distribution. Third type is the state based type, where it is discrete model or continuous model. Discrete model assumes the system state changes abruptly at specific times, such as traffic light, whereas in the continuous models, it assumes the smooth changes over time, like tracking car following model. So, these are the different types of the simulation models depending upon what analysis or what we need to test, we choose the model. Now coming to the levels of traffic flow modeling. So traffic flow can be modeled at different levels of details. First is the macroscopic. This is aggregate view. Traffic is treated like a fluid using volume, speed, and density. It it is suitable for analyzing entire urban or metropolitan region. Then the second level is the mesoscopic. Here it is the intermediate level. Vehicles may be grouped into platoons or simplified vehicle dynamics are considered. So it balances both the breadth and the detail. Now coming a third level, that is a microscopic, where this models individual vehicle behavior, including the acceleration, deceleration, lane changing. So it deals for it's ideal for the detailed analysis of intersection or corridor. So these are the three levels of traffic flow modeling, that is macroscopic, mesoscopic, and microscopic. In the macroscopic, we deal with mainly with the macroscopic parameters such as volume, speed, density. Mesoscopic lies in between the both of them, whereas microscopic deals with the individual traffic. Individual driver behavior includes the microscopic parameters analysis. Now coming to analytical versus simulation approach. So, if the model is simple and we can solve it analytically, giving an exact solution, but the traffic system are very complex with many interacting entities. In such cases simulation is used. We used only analytical solution when we have the exact solution that is possible, and if the model is simple. But traffic, it is a complex system where different vehicle interact with each other, and also with the infrastructures. Therefore, it is a very complex system. Therefore, we use a simulation method. So, where simulation let us perform the numerical experiments on computers, often include stochastic characteristics. Traffic microsimulation allow us to evaluate system performance under different scenarios, helping make informed decisions without risking real world disruption. Therefore, in our traffic, we may mostly use the simulation approach rather than the analytical solution. Okay, so now starting with the traffic micro simulation. So, so essentially, the this models the interaction between the physical traffic system like route, intersection, signals, and the users that are vehicles and drivers. So the infrastructures are supply, whereas the users or drivers are the demand. So why do we call as the micro? Because it works at the individual level, tracking each vehicle or person, and by simulation because it models the internal process, not just the end results. For example, how driver decides to overtake or how signal affects the vehicle flow. Therefore, that's the reason we call it traffic micro simulation. So, traditionally, macro or even micro models often cannot handle complex traffic situations. That's why micro simulation is so powerful that it allows us to model traffic behavior realistically and evaluate different traffic strategies. So now we were discussing about how this traffic simulation, micro simulation works. So it has inputs that are supply and demand. So starting with the supply. So supply inputs are the elements controlled by the traffic managers that are physical attributes or physical infrastructures like road, intersection, signals, which we represent using our nodes and links. And operating strategies such as signal timings or lane configuration or the traffic rules. So these are mainly the supply input that are controlled by traffic managers, whereas on the demand side we have input, input travel demand. This is usually represented in terms of the origin and destination matrix, or also known as OD matrices. So here we have the origin and destination of particular driver, along with vehicle type, then driver characteristics, what is its reaction time, whether the driver is more aggressive or not. We have the demand that can be static, whether we need it for a particular peak hour simulation, or dynamic, that is that varies over the simulation time if we are doing the time dependent traffic analysis. And some model allows us to enter demand as link volume and the turning percentages, so which is easier to measure in the field. So these are the input, demand, and the supply. Now coming to the micro simulation model and process, that is step 2, how we model them. And third will be the output. So input, then the model, and the output. So here we are in the step 2. So once the inputs are set, we run the micro simulation. The user define the simulation time, that is mostly about 1 to 2 hours. The model progresses in these small increment steps, capturing how vehicles interact with each other and with the infrastructures. If we input a total number of vehicles, the model can internally generate individual vehicle using probability distribution, assigning speeds, departure time, and other characteristics. This ensures the realistic variability in traffic flow. The micro simulation model also captures all the interactions between the vehicle to vehicle, whether the vehicle is merging, lane changing, or vehicle infrastructure, whether it is stopping at signal, moving through intersection. So this is what it makes it so powerful for evaluating for the realistic traffic behavior and network performance. And then we get the output once we run the model. So microscopic models provide data at three levels. One is vehicle level, then the intersection level, and the system level. So in the vehicle level statistics like speed, travel time, link uh, is being given. Then at intersection level, we get matrices such as congestion, delay, turning movements, and this system level, we get the aggregates like the average speed, total delay, level of service. So these are the uh, output parameters or aggregate matrix. Many aspects of a traffic like driver behavior or vehicle arrival are modeled as random variables. You can define parameters like mean and variance, but the model also handles much of this internally. Though we can give it, but if we are not giving it, model internally handles these conditions and then give the output. And these models are based upon the car following models that we have just discussed earlier. Some maybe some simulation model is based upon the General Motors, some may be based upon the Winderman car following theory. So depending upon how the simulators or the simulation model has been designed, based upon which theory these give outputs on based upon that theory. And the visualization is one of the most important features. It allows decision makers and public to see traffic movement in real time, such as lane change or overtaking. It also allows us to test scenarios like adding a bus lane or changing a signal, plan or observe the effect on traffic flow. So here if we want to design, so this is in terms of the designing. So if we want to add new bus lane and see its effect on the traffic flow, we can't do directly on the real world condition. It after developing or constructing a bus lane, we can't see whether it will be advantages or disadvantages or how much effect it will give to traffic flow. But if we do it in the simulation process, it is cost effective, risk free. We can actually model it in the simulator, see if it gives the positive effect, we can do it in the real world, else we can opt out. So these caution is that user must ensure model behavior is realistic, avoid treating model as a black box. So because these simulation models are based upon different car following theories that follows the realistic traffic behavior, therefore we should not consider these model as a black box, rather consider it as a realistic driver behavior. So once we get this output, this the next step is the model verification. So once the simulation runs, we must ensure it is producing realistic results. So this is done through verification, calibration, and validation. So in the verification is the process of checking whether the simulation correctly implements the logic defined by the model developer. Whatever the model developer has given the logic, does the simulation is correctly implementing or not. So, for example, if a vehicle arrives are assumed to follow a Poisson distribution, verification ensures that the generated vehicle in the simulation actually follows that distribution. So, it is important to note that verification does not evaluate whether the assumption itself is correct or not. We don't say whether the Poisson distribution assumption is correct or not, but uh, instead, we are only checking whether the model faithfully replicates the logic or assumptions that are intended to be implemented. So, verification is a critical step before we move on to the calibration and the validation. It ensures that the model is behaving as it has been designed so that any subsequent analysis or decision based on simulation are reliable. So, after verifying whether it is actually implements the logic that has been set by developer or not. We go to the next step, that is calibration. So calibration is uh, essentially about adjusting the micro simulation parameters so that model replicates observed traffic condition as closely as possible. So, so why do we calibrate? Uh, well, traffic flow, driver behavior, and control operations vary by location and by the objective of our study. Are we simulating an intersection, a corridor, or even evaluating the emission? So, calibration ensures the model is realistic in that specific local context. So, here the key point is calibration is always done before validation, and we must use separate dataset for calibration and validation to avoid biasness. So the the calibration is mainly done to adjust the microsimulation parameters that could replicate the traffic conditions more accurately. So the process involves selecting sites, whether we have to simulate the intersection or corridor, then define performance measures, whether like average speed, travel time, or delay, then collect empirical data from the sites where we will be calibrating the model. So we will have to collect the empirical data from different sites, then initialize model parameters. We give default values depending on past calibration or the judgment. Then run the simulation and compare the output with the field data. So here we compare with the and adjust it so that it is similar to the traffic condition. Now, coming to the parameter, how we select these in the calibration step, parameter selection and iterative adjustment. So, the microscopic models can have 30 or more parameters that are related to vehicle or driver characteristics. So we don't tweak all of them. It's too complex. So instead we focus on parameters that are highly sensitive to our performance measures. So we mainly focus on some of these parameters. So calibration is iterative. We adjust parameter, run the simulation, compare the results with the field data. We repeat this step again and again until the output match the observed traffic condition within all acceptable tolerance. So the optimization methods like trial and error, genetic algorithms can help make it this process more efficient. So the goal is efficient calibration while keeping the process manageable. If we try to calibrate all the 30 plus or whatever the number of parameters are, it will be too complex. So we just select some of them, adjust that until it matches the observed data in the field within all the tolerance limit, and then we use the calibrated model. The next step is model validation. So once we have the calibrated model, the next step is validation. Validation checks whether the calibrated model actually captures the fundamental traffic relationship accurately or not. So we use a independent data set that we have not used in the calibration step. And since both field and simulation data are stochastic in nature, meaning they are variable, multiple simulation runs with different random seeds are necessary. These run help us to estimate the central tendency and dispersion of the outputs and ensure that the model behavior is realistic and reliable. So these are the steps. Firstly, we take the input, run the model, get the output, then we do model verification, calibration, and validation. Then the statistical analysis of the output. So even After the validation, we need to ensure that the simulation outputs are statistically valid. We can compare outputs with three sources. So, to make sure that the simulated model is not giving any random, maybe the simulation model for a particular signal is giving like 200 or 300 vehicle kilometer speed. So, that is not a valid uh, output. So to do the so for that, to check it whether statistically it's valid or not, or whether the variance given by the model is correct or not, we do the statistical analysis. So it has three sources. First is theoretical or deterministic values, where values like capacities from manual guidelines have been checked. Then the empirical field data collected on sites, we check it using the field data or the manual or the other simulation scenarios, or output from the different simulated scenarios. So this help us to compare the statistical output of the model. And we also calculate statistically optimal number of simulation runs using t statistics, allowable error, and estimated standard deviations. So this ensures our conclusions are robust and are not based upon the random fluctuations. So to quantify how well simulation matches the real world data, we use aggregate goodness of fit measures. So these combine multiple performance measure into single matrix. Three common matrices are MAE, that is mean absolute error, uh, that is 1 by n, summation of a difference between the observed and the field data, then the experimental data. Then we have a map, that is mean absolute percentage error. Then we have the RMSE, that is root mean squared error. So here OI is the observed value, whereas EI is the simulated value. So these measures help us see whether the model is close enough to reality, or either in absolute terms or relative to the field data. So the choice of the absolute versus the relative accuracy depends upon what is the application. So if these are the conditions, so if we are using the absolute accuracy, that is mainly critical when we need to extract the exact numbers like control delay at an intersection, whereas relative accuracy matters when we are comparing alternative strategies such as different roadway design or signal plans. So we do not need exact performance measures. We just want to model to correctly rank which design performs better than the others. So in that condition, we use relative accuracy, whereas if we need the exact numbers, we use the absolute accuracy. So applications differ. Traffic of operations needs the traffic operations such as signal timing, travel time needs the absolute values accuracy, while the roadway design, that is merge conditions or the evaluation in terms of delay or fuel consumption or investment scenarios, these all needs mainly rely on the relative accuracy. Depending upon what is the use case, we use the absolute or relative model accuracy. Then comes the performance measures. So performance measures are simply simplify, quantify, and communicate the results. They allow decision makers like policymakers to understand the outcome without needing the technical details of vehicle interactions. So there are different types of performance measure. First is point based, that is spot speed or throughput at a specific location. Then a link based, that is travel time, average speed or delay on the road segment. Then the corridor or system based, where overall average vehicle or person speed or total delay is being used depending upon what is the type. These are different types of the performance measures. So depending on what we need, we use that as the measure. Choosing the right performance measure depends upon the objective and context. So this we combine it with the goodness of fit matrix and accuracy evaluation for reliable and actionable outputs. So the key takeaways was, after we get the output, after doing the taking the input that in terms of supply and demand, doing the micro simulation, getting the output, the main step after that to be applied are first model verification. This ensures that the simulation logic replicates what the developer has intended, that is the distribution of rules. Then is calibration, adjust the parameters to match the field condition. Then validation, that confirms that the calibrated model actually accurately captures the real world traffic relationship. Then statistical analysis, that confirms outputs are reliable and determines optimal simulation runs. Then goodness of fit, that is uses the matrix such as MAE, MAPE, RMSE to quantify map model accuracy, and depending upon whether we need the exact number or comparison between alternative, we use the absolute or the relative accuracy. Then the performance measure, selecting the point, link, or system level measures based upon the objective. So these steps ensures that the micro simulation inputs are realistic. Micro simulation outputs are realistic, reliable, and useful for traffic analysis and planning. So this was all about the summary of week 9. If you have any doubt, please let me know. Else, we will discuss some of the questions. Okay, so since there's no doubt, so we'll start with the practice questions. So this is the common data for some of the following questions. So the data is the leading vehicle and the following vehicle are traveling with a speed of 20 meter per second and space headway of 27 meter. At t is equals to 1 second, the vehicle accelerate by 1.2 meter per second square for 2 seconds. Simulate the behavior, that is acceleration, speed and position of the following vehicle using General Motors first car following model, and assume sensitivity coefficient as zero point 0.5 per second, reaction time 1.5 second and update interval zero point 0.5 seconds. So this is the common data for series of the questions. So the questions that are to be answered using this data are: first is, what is the speed of the lead vehicle at t is equals to 3 seconds? What is the distance headway in meter between lead vehicle and following vehicle at t is equals to 3 seconds? What is acceleration of the following vehicle at t is equals to 3 seconds? Then what is the speed of following vehicle at t is equals to 3.5 seconds? And what is the position of the following vehicle in meter at t is equals to 3.5 seconds? So first try to answer the first two questions. So first we will discuss the first two questions and then we will discuss the next three questions. Okay, so let's discuss the solution for the first and second question. So, question 1 was to find the speed of the late vehicle at t is equals to 3 seconds. So, the initial speed that was given was 20 meter per second. As you can see in the question, the initial speed is 20, space headway is 27, and the acceleration is 1.2, and acceleration duration is 2 seconds. So, from t is equals to 1 to 3 seconds, that is in the question. So the speed is equals to 20, that was initial speed, plus the acceleration into the duration. So we get 22.4 meter per second. So this is the speed of the leading vehicle. And the second question was to find the distance headway between the lead vehicle and following vehicle at t is equals to 3 seconds. So initial headway was 27 meter. Reaction time was 1.5 seconds. That was given in the question. So following the vehicle starts reacting at 2.5 seconds. In the question it will begin, update interval is zero point 0.5 and reaction time is 1.5 seconds. So the distance traveled by lead vehicle from t is equals to 1 second to 3 seconds, that is 2 seconds. So the distance traveled by lead vehicle is calculated by 20 into 2 plus 0.5 into 1.2 plus 2 square, that is Vt plus half At square. So V is 20, time is 2 seconds plus half, that is 0.2, and the At square, so A is 1.2 and T is 2. So we get 40 plus 2.4, we get 42.4 meter. Then distance traveled by the following vehicle. So at 1 to 2.5 seconds, that is delta t is equals to 1.5 second, constant speed of 20. So as following is 20 into 1.5, that is 30 meter. And from 2.5 to 3 seconds, when the reaction has happened, starts to accelerate. So accelerator is equals to half into vehicle lead minus vehicle following, because 0.5 was the, because acceleration is given using the General Motors car following model is alpha times the ln alpha is given as 0.5 distance between these. So it will be 0.5 into 22.4, that was the leading vehicle speed, and the following vehicle is 20, it is 1.2 meter per second square, and distance covered in 0.5 second is 20. Similarly, half base into height, we get half base. Here the A is changed to AF, that is 1.2, that is for the following vehicle. So this one was for the leading vehicle, this is for the following vehicle. So it is 10.15 meters. So total distance covered by the following vehicle is 30 plus 10.5, and total distance covered by the leading vehicle is 42.4. So the distance headway t is equals to 3 seconds is equals to 27 plus 42.4 minus 40.15. 27 was the initial headway that was being given. So 27 plus 42.4 minus 40 is 29.25 meter is the distance headway. T is equals to 3 seconds. So rounding it to the 1 decimal, we get 29.3 meter. So this is the solution for the calculating the distance headway between the leading vehicle and following vehicle. Now try to solve this question, that is acceleration of following vehicle, speed of the following vehicle, and the position of the following vehicle using the same data. Okay, so let's now discuss the next three questions that is to be solved using the same data. So the first question was to find the acceleration of the following vehicle at t is equals to 3 seconds. So using the car following model, the formula is the acceleration is equals to sensitivity into the uh, relative speed between the following and the uh, leading vehicle. So we have the following vehicle speed at 3 is equals to 3 seconds as 20 plus 0.5 into 1.2, that is 20.6 meter per second. Then we have the lead vehicle that we have already calculated at 3 is equals to t is equals to 3 second as 22.4, and we put them in the General Motors model equation that was given as this, and we get the acceleration for the following vehicle as 0.5 multiplied by 22.4 minus 20.6, and we get as 0.9 meter per second square. Next question was to find the speed of the following vehicle at t is equals to 3.5 seconds. So acceleration at t is equals to 3 seconds was 0.9. We have already found. At t is equals to 0.5 second, that is the we have to find the speed changes. So v following is equals to 20.6, that was the speed at 3 seconds, then plus 0.9, that is acceleration, into zero point 0.5, that is the time that we have to find out. So it is 20.6 into 0.45, that is 21.05 meter per second. If we round it about, then we get 21.1 meter per second. And the next question was to find the position of following vehicle in meter at t is equals to 3.5 seconds if initial position is 0 meter. So if we have to find it, the position of following vehicle at t is equals to 3.5 seconds. So at t is equals to 0.0 to 1 second, speed is 20 meter per second and distance is 20 meter for 0 to 1 second. Okay. Then because we do speed into as we apply it here and we get 20, then at t is equals to 1.2 from 1 second to 2.5 seconds, speed is 20 meter per second, distance will be 20 into 1.5 equals to 30 meter. Then from 2.5 to 3 second, acceleration is 1.2 meter per second square, and uh, that we have calculated here at 3 seconds, and the initial speed is 20. So in distance we get at 20 into 0.5 plus uh, 0.5 into, that is ut plus half at square, so u into t plus half a is 1.2 into t square, we get it as 10.15 meter. Then for 3 to 3.5 seconds, uh, till here, that 3 second thing we have already calculated, that was coming out to be 30 plus 40.15, that is for from time 1 to 3 seconds we get is 40.15, that is similar. And plus we add the 20 meter, because here we have taken initial headway as 27, but here we have uh, it has taken as initial position as 0 meter. So then we have calculated using and multiply 20 into 1, we get 20. And then for 3 to 3.5 we apply similarly, we have the acceleration here as 0.9, so we applied ut plus half at square to get the distance at for time 3 to 3.5 seconds as 10.41. Then we add the distance traveled for each of the time duration, we get it as 20 plus 30 plus 10.15 plus 10.41 as 70.56 meter. So the answer is making it round to one integer, one decimal place, we get as 70.6 meter. So this is the solution for the questions that was based upon that the common data that was given here based on the General Motors first car following model. I hope there is no doubt, so we can continue and go to the next question. So the next question is, which of the following statements are true with respect to Windman car following model? First is car where sorry First is faster vehicle approaching a leader will de-accelerate if SDV threshold is crossed. If the SDV speed difference threshold, then if relative distance between leader and following vehicle is SDX more than SDX, then driver follows leader without consciously deaccelerating or accelerating. So this is speed um, uh, space difference. Then faster vehicle approaching a leader will accelerate if Bx threshold is crossed, and if relative distance delta x becomes less than Ax threshold, it will result in collision. Okay, so here to make it clear, SDV is the speed difference threshold, SDX is the distance threshold, and AX is the following threshold, and the BX is the braking threshold. So faster vehicle approaching a leader will de-accelerate if the speed difference threshold is crossed, and if relative distance between leader and following vehicle is more than SDX, then SDX means the safety distance, relative distance, a threshold, then driver follows leader without consciously leading or accelerating, and faster vehicle approaching a leader will accelerate if Bx, that is braking threshold, is crossed. If the relative distance, that is delta x, become less than the Ax is the following threshold, it will result in collision. So which of the following are true? So let's discuss the solution of this question. So first statement was faster vehicle approaching a leader will de-accelerate rate if SDV threshold is crossed. That is correct. If the threshold has been crossed, and the faster moving vehicle will de-accelerate. So it is correct. If relative distance between leader and following is more than the safe distance, then the driver follows leader without cautiously de-accelerating or accelerating. That is wrong because it's too absolute. The driver may still accelerate or de-accelerate slightly because the distance is more. So that is incorrect. And faster vehicle approaching a leader will accelerate if the BX threshold is crossed. That is also not correct. If the braking threshold is crossed, why will the faster approaching will lead a leader will accelerate. Then if relative distance, that is delta x, becomes less than the ax threshold, it will result in collision. That is also correct. If the relative distance is less than the critical distance, a collision may be happen. That may be possible. So the correct answer are A and D. That are the correct statements with respect to um, Wiedemann car following model. Now coming to the next question, that is accept or reject the statement lane change behavior of model can be modeled in microsimulation model. A, accept, or B, reject. Okay, so now let's discuss the answer to this question. So, micro simulation models like Windeman or the other microscopic models like car following models can simulate the lane changing behavior of individual vehicle, and these models use the rules for gap acceptance, desire to overtake or change lanes based upon the speed difference, driver aggressiveness or route choices, and also based upon the safety threshold that ensures there is minimum distance between the vehicle and the target lane. So thus, the lane changing is explicitly modeled in the micro simulation along with car following. Therefore, we accept the statement. So so these are the all the practice questions for week 9. If you have any doubt, we can discuss it now. Hello, we can be audible. Can you please write your questions in the chat box? We are ending the session now. So, thank you everyone for joining the session, and we will meet again in the next week problem solving session. Thank you.